Good morning and good afternoon to Professor Saad. I welcome you back to the on the day two of the CAM course on hybrid renewable energy system and microgrids. We continued yesterday discussion on the microgrid technology by Professor Saad. I welcome you, Professor Saad. You can take over and take over the lecture. Professor Saad?
Yeah. I'm just trying to put it on the slide mode show.
Okay.
Yeah. All right. Can you see now?
Yeah, it is not in the presentation mode.
Oh, the same problem like yesterday.
Yeah.
So try this way. So let me try. Can you see now? My screen?
Yes. Yeah. Slides is not.
How about now?
You can go for other.
Scale full screen.
You can go to the other screen first, sir. There is an option, is there? Yeah. Fine.
Okay, that's good.
But,
So now it looks.
next slide is also simple.
Just need to get the screen duplicate.
Yeah, it's fine.
Yeah. Okay, so good morning, everyone. So we are going to continue where we stopped yesterday. So I think yesterday, just to recap what we discussed yesterday, we look into the traditional grid. What are the issues with traditional grids? And then we look into the new or the current grid, the concepts, which actually it's evolving, still evolving. And then we define what is a microgrid, okay? And the issues or some of the issues and why do we need microgrid, and then the benefits of microgrid, some of the issues of microgrids, and where this microgrid can be installed, and the main components of the microgrid. I think that's where we stopped yesterday. So just as a recap, so this is a typical structure of microgrid, and doesn't mean it have to have all these components, but some of these components are required in this microgrid to work. So I think one of the main reasons of using microgrids is to make use of the renewable energy resources. And what I said before, I think I mentioned before yesterday, one of them is the photovoltaic, okay? the wind, if we have. And this is what I mentioned yesterday about micro hydro or run of river. You can see this is a micro hydro system, which actually can be used as a part of the system. So these are some of the resources or renewable energy resources that we can go. So the mode of operation of microgrid can be in two. Either it is grid connected or it is islanded microgrid. So depends on the location and depends also on the design objectives. Like I said before, depends on also always on the design objectives. So grid connected, it's useful and it's good when you have access to the grid, and that may help to lower the storage size. Okay, and also it can help also inject the extra power to the grid. Islanded microgrids usually are designed for islands, for remote areas where the grid is not available, or remote CAM or natural disasters, where we have, for example, flood or fire or whatever. So we need the electricity. So that's most of the time it's an isolated or an army CAM, whatever. So these are the two mode of operations of the microgrid. So let's look into the grid connected. So if you look into the grid connected, you can see actually the grid is there. So the grid is here, and then we have this PCC. Okay, this is the PCC is the point of common coupling. Okay, and this point of common coupling it's meant for to connect to the grid system. So every system that have connected to the grid, they have this PCC. Okay. And on the other hand, okay, where you can have the variety of distributed renewable energy sources. For example, here look into the renewables. For example, we have PV, we have wind, okay, as a source, and then we have the electric vehicles, okay. And you can see here these boxes, as we discussed yesterday. This here, the brown boxes here, or these boxes. These are the power electronics devices, and in different, for example, in EV, for example, you need a DC to DC converter, okay, and then you wanted to connect it to the here, the blue line here, this blue line, it's an AC bus, okay. So for example, PV is also DC, so you can see I have a DC converter and then connect it to this DC bus and then connect to an inverter, which is a DC to AC, and then connect to the AC bus, okay. The wind turbines is the same. So wind turbine, it's what you call a rectifier, AC to DC, and then from DC to AC, and then connect to the AC bus. Okay, the same things. You may have multiple sources like PV here, batteries. So you need an inverter. Okay, you may have also compressed air. Okay, so as a source, so you can inject to the AC bus, and then you can see here, this is a DC coupled subsystem. You can see here, this is a DC coupled subsystem where all of it is operating on a DC. Okay, so that's why you may have some subsystems, like here we have the household appliances, like all the electronics, all they can operate on DC. And then we have, for example, the flywheel, the EV, the PV. So this is like a subsystem. But in order for you to communicate with the AC bus, okay, so you need to have the inverter, which able you to connect you to the system. Okay. All right. Any questions here for grid connected?
No, Professor.
Right? Okay, so in islanded microgrids, so we don't have the utility anymore. We don't have the grid anymore in the system. So the grid is not a part of the system. So what have here? We have like
also it can be a combination, as I said before. It's not necessary to have all of those, but it can be like here. It is an AC microgrid, okay? But you can see here, this is like a subsystem, or we can this is a subsystem which operated fully on a DC, okay? And here you don't have the PCC, you don't have to connect to the grids. All right. So what you need here, you need to energy management of all those sources, you know, to manage the sources and the loads. Okay. Okay. The microgrid configurations. Okay. So we have seen the two mode of operations. They can operate on a grid connected or islanded. Now, the configurations. Okay. The configurations, it can be AC microgrids, DC microgrids, hybrid AC DC microgrid means it is a combination of two microgrids. One is AC, one is DC, and then we have interconnected microgrids. So these are the different configurations that can be, you know, or can configure. Or, for example, when we want to, we go back again to the objective of the design. So what's the objective of design? You know, so that's very important, you know. And then based on that, we will decide actually, are we going to go for AC microgrids? Okay, are we going to have for DC microgrid? For example, if you have all your loads are AC, so that it will be a good choice to have an AC microgrid, and you are connected to the grid. So that is good options, for example, because the question is which one we are going to select in these configurations. Do we have to select AC microgrids or DC or hybrid? So the answer to this is, if you have most of your loads are AC and you are connected to the grid, I think that is a very strong reason to have an AC microgrid. Okay? And then also depend on the resources that you have. For example, if you have some resources which are a DC or AC, supply AC, then it's a good also option to have an AC microgrid. If you have most of your loads are DC and most of your sources are DC, like photovoltaics, for example, like batteries, okay? So that is another good reasons also to have a DC microgrid. Sometimes you may have a hybrid, so you may have a combination of the two, but in this combination, you need a bidirectional converter which works, you know, between the loads and the sources. And also we may have interconnected. Interconnected microgrid means we may have a large number of grids. Microgrids are interconnected with each other. Okay, so let's start with the AC microgrid. Okay, so the first one is we have a typical AC bus system. You can see here we have a DC AC bus systems. And then we have the PCC, the point of common coupling, and that's connected to the grid. And then you can see just now, once you have a grid, there is a strong reason for you to have an AC microgrid. So, and you can see here, all of them are converted. For example, batteries, wind, example, and this is the loads, and then we have other loads which actually. Most of them, for example, here AC loads. Okay, so that's how you decide actually what will be the best configuration for your system. Okay, all right, and then we have also we can configure our microgrid into DC microgrids, and then if you look into here, for example. Most of our loads are DC here. For example, here some of the loads are DC. Okay, these loads are DC, and then we have a lot of this is DC PV. Electric vehicle is DC. You know, and you can see that's actually more components what you call having AC, and then also here the wind turbines. Also, wind turbines actually can operate on DC because you just need a rectifier. Okay, but if you want to have a grid connected, then you will have this what I call a grid interfacing converter. Actually, that helps you to hook to the grid system. Okay, is it clear?
Yes, Professor.
I don't know. Am I audible? Anyone in
You're audible, Professor.
Huh?
Yes.
Is it clear? Hello?
Yeah, you're audible, Professor.
I cannot hear you.
You're audible, Professor.
Audible.
Yeah.
Sorry?
I'm audible. You're audible, Professor.
I don't know. Anyone? I cannot hear you. Can anyone confirm that you are seeing the right slide and you can hear me clearly? Anyone can confirm that? Please.
What is happening?
I'm explaining the DC microgrid. When you can see the DC microgrid. Anyone here can confirm that?
Yeah, you're audible, Professor.
Hello? Okay, I assume that everyone is seeing. Please let me know. If what do you call? If you cannot see or you cannot hear me clearly. Okay. And also, like I said just now, we may have a hybrid AC DC microgrid. Okay, you may see AC. So what we have here, we have a combination of 3 microgrids here. Okay, where we have an AC microgrid, a DC microgrid here, another DC microgrid here. So total of 3 microgrids. Okay, and then in order for us to communicate with each other, with each grid, for example, from DC to AC, you need this inverter. And also this inverter, one of the main characteristics of this, it has to be bidirectional. Okay, and this one also. Okay, these interlinking converters have to be bidirectional because power should be able to flow from one microgrid to another microgrid. For example, yeah, we can see here we have 2 DC microgrids, but they have to go through the AC bus, so they are connected through the AC bus. So that's how the configuration actually of hybrid microgrids looks like. Okay, and that's actually useful, as I said before, especially for you have, for example, 2 communities when they have 2 different grids, and maybe sometimes you may have even in what you call spaceship, or in what you call all these marine ships, so they will have this kind of configuration. So they will have DC microgrids, AC microgrids, and then they will connect them and to share the power in case it's needed by one of the loads or microgrids. Okay, and we have the interconnected. Okay, the interconnected microgrid. So what you can see here, if you look into here, what you can see, if you see the first microgrid here, the microgrid number 1, and then we have microgrid number 2. Okay, and then you can see we can have 3, 4, 5, 6, 7, 8, whatever. You can have many as you want. And then you can see here the interconnections. You see they have the battery here that is connected to this AC bus, and then here another what you call PV, and then connected to the AC bus through an inverter here, and then we have another diesel generator. This has a diesel generator, okay, and is connected to the AC bus, and then we have another microgrid here also, but this microgrid does not have a diesel generator. And you can see we have 2 types of load. One of them is the AC load, the normal AC load. Another one is what you call the critical load. So the same thing here, and then they are connected to the grid, to the main supply, which is the grid here. So what happened here? If you look into here, these 2 are connected. This microgrid are connected through this breaker. Okay. So what does this mean? Okay, let's see. They can.
Professor, we are not audible to your voice.
Mute.
Huh?
Muted.
Professor,
Mutual loss.
Professor, excuse me. Hello. Professor, you're in mute position. Can you unmute yourself? Yeah, it was, I don't know how it has happened. Not all the way, just within a minute, I think it has happened.
How about now?
Yeah, now.
Can you hear me now?
Yeah, I can hear. Yep.
Yeah, that's why I was asking. Is there any questions? Anyone have any questions of the previous slides?
No, actually, all the other attendees are become a viewers. They can't unmute themselves. Maybe they can
until
post
the end.
in chat box. I think so. We can make that
Okay.
option. Okay, Professor.
Okay, thank you. But if you have any questions, please let me know. Okay, so maybe you can read the chat box and let me know. Okay.
Yeah. Okay.
All right. Thank you.
Okay, go ahead.
Okay. I hope now everyone can see the slide. So some of the advantages of the hybrid, when you're having a hybrid microgrid, see, reduce the investment costs because reducing the number of electronic power converters. So this is the advantages of a hybrid because we've seen few types of microgrids, but one of the good things about this hybrid is reducing the number of power converters. Because you will have, if DC, then all the loads are connected to DC, so you don't need a converter for them. And then minimize the conversion losses. Yeah, because every time, if we add a converter, okay, there will be a losses. So by having a hybrid, then we will have eliminating these losses. Enhance the nodal reliability because of the availability of alternatives. So we have a lot of resource available which can be used. And maximize utilizations of renewable. So because the objective, as I said before, one of the main objective is to have maximization, or we call it a renewable energy factor as high as possible. Okay. And as mentioned before, when you have a hybrid grid or hybrid microgrid, you see here the BDC, the bidirectional converter. Okay, this bidirectional converter between the AC, it's very important, and it should be able to move the power from one side to another side. And you can see here, this is an AC bus, this is a DC bus, and then it is connected to the grid. I'm not going to go into these equations. Okay, yeah, these are some of application, as I think mentioned yesterday. So, for example, campus environments, which some of universities have. We have a remote off grids, which is mainly off grids, and then we have military.
Professor.
So, what are the categories based on power? I think that's what one of yesterday of questions. The commercial and industrial microgrids. So, for commercial, usually more than 50 kilowatts. And it typically operate on a three-phase, okay?
Professor.
And functionality can be expanded. Community or campus between 1 to 1 megawatts, okay?
Professor.
And also can be a modular or single ratings. Or you can have also a utility scale, which is more than 10 megawatts using multiple interconnected microgrids, okay? So, and then some technical advantages. I think I mentioned this about yesterday, so I don't have to. And I think we didn't mention about this. So the operation and the investment issues, reduction of the physical electrical distance, because we don't have to do the wire extension for transmission lines, and reduces transmission losses. Resilience and reliability. Okay,
Professor?
that actually will help to improve the resilience and the reliability of the power because it's become decentralized supplies. Okay, because it decentralized control, better matching the demand because it's close to the load, it's matching the demand, reducing of the large transmissions, and also the reduction of downtime. This is in terms of technical capabilities. Okay, I think yesterday also we discussed some of these issues, which is the bidirectional power flow. Okay, so all this microgrid, especially if you have a hybrid, you have power directional power flow, which have to be in work. Okay, sometimes we have local oscillations which emerge within the units of microgrid. Disadvantages: low inertia, yeah, because mainly dependent on renewables, so it has a low inertia. Okay, so hello, sorry, I'm muted.
No, it's audible, sir. You are audible.
You are audible, sir.
How about now?
No, yeah, you were audible continuously.
How about now?
Yeah, audible.
This one? Have you seen this?
Yes.
Sir, display setting need to be changed, sir.
You just change that slide display.
Well, I don't know why. I'm on slide. I'm on full screen now. Full mode. I can see the slides.
Sorry, you are needed to duplicate your slide.
Okay, let me try to stop this. Stop sharing. Stop presenting. Okay. See what? I think maybe turn on this one and then present. So I present the full window, right? Okay, share. Okay, and then can you see my slide now? How it now? Works? Is it working now?
Slide is not visible, sir.
But in my side, it's coming, it's full. Stop sharing.
We can see the Chrome window.
Okay. Let me try this. Sharing entire screen. Okay, and then share. Okay, can you see my screen now? Okay. How about the presentation now? Can you see the presentation?
Yes.
Okay, so what I'm going to do, I'm going to click.
Yeah.
I click on the presentation mode.
Yeah.
How about now?
Actually, now we are seeing the next slide also. That annotation is coming. That's why. Main slide along with that next slide also is visible.
So there is a display setting, sir.
Okay.
Yes.
Yeah.
Duplicate the slide, so.
Second one.
Second one.
Okay.
Duplicate the
How about
slide.
now?
Yeah.
Now it's okay, sir. You can go ahead.
So I don't know. Yeah, because I have two PowerPoints, so I can switch. I want to switch sometimes from this, So is it okay?
Okay. Now we can go ahead.
Okay. I'm not sure. You have seen this before?
No, earlier there was a next slide was also getting up.
Yeah.
This one.
Yeah, this one and all.
This one. This, have you seen this? Okay. Okay. Thank you. So apologies, something I think, I don't know, this Google Meet, I'm not sure, maybe I don't know how to use it, but
Fine.
most of the time we use Zoom and what you call Teams,
Okay.
I hope now it works. So as I said before, commercial and industrial, so the range based on more than 50 kilowatts, so it's three-phase and can be expanded. Campus or community, usually between 1 to 10 megawatts, and it's modular in nature. Utility scale usually greater than 10 megawatts. And I think the environmental issues we have discussed yesterday, and operation, the resilience. So one of the good things about this, like I mentioned yesterday, it is decentralized, so very easy to control. It matches the load to demand, okay? And then also the reduction of the transmission lines and also the downtime, because it's it's localized and things. There are, in spite of potential benefits, actually, of development, suffers from several also challenges. One of them is the bidirectional, power flow. So this have to be very controlled, Okay, so this is not it's not as straightforward as easy. So you have when you have power flows from one side to another side, then it's and also stability issues, okay, because you have, for example, the wind less, or the solar is less, or the battery is low, the state of charge of the battery, and so on. Also the low inertia, because there is no inertia in the microgrid. Most of them are renewables and batteries, so maybe you have a what you call diesel generators, but so I think the most recently, which is the grid forming, okay, instead of grid following, virtual inertia devices, so to provide a response for low inertia systems, okay. Yeah, I think yesterday we discussed about the high capital costs, okay, and many problems actually with the administration, and the legality of this kind of microgrid. So when who own it? If it is a community, who own the community? Is it the government? Is it the municipality? Who maintain it? Who this? There are a lot of what I call legal and administrative constraints that need to be addressed while deploying on this kind of microgrid, especially when it is on the community. For example, the land that they use, the electricity that is sold, and so on and so on. Okay, and also market monopoly. So I think this is also another issue. So in some countries, there is certain companies which manipulate this power sector. So it's very hard to penetrate, or maybe very expensive to implement. Okay, in terms of the hierarchy control of the microgrid, okay, so we have primarily 3 levels, okay, of control, which is the tertiary control, and then the secondary control, and then the primary control, okay. So, and each one of them, communicate with each other, So, for example, the tertiary control will be looking into the optimal operations on both mode, grid connected or isolated. Power flow control. Secondary control looking into compensating the voltage deviations, and the consumption, I call the compensation of the frequency. And then also we have the primary control, which is the voltage stability, frequency stability, and plug and play capability of I call distributed renewable energy systems. Yeah, I think that's we will come to this later. I think maybe, yeah. Just now we're talking about the networked microgrids. So this is how it looks like. So when you're having a interconnected microgrids, so this is how what you call it looks like. So can support and exchange power with each other. They are highly desirable when utility are not accessible. So because, for example, you have maybe a community here, you have another community here, you know, and then you may have also even communication, data communication, or cyber, or even sometimes physical communications. Okay, and through this, you will have economic energy exchange. Okay, means one microgrid generate more, another will generate less. Tomorrow it will be the opposite, and so on and so on. So, and the energy support of for self-healing capabilities, and that's what I mentioned before. Okay, which is the self-healing capabilities. The concept of self-healing capabilities is very important when you have a network of what you call microgrids. Okay. Okay. Any questions so far? Anyone? I'm not sure if you have any questions, or can you see the slides? Anyone? I don't know. I don't know.
There is a question in the chat box.
The networked microgrids. Can you confirm, please?
Yes. Hello.
I'm not sure.
Maybe you can select your. Hello, Professor.
Maybe you can remove this one here, and you can just operate on this. Much easier. Okay, I think maybe now we go back to the other slides. Discard. So go back to the examples. Okay, so some of the examples. Let's take some of the examples. Some examples where these microgrids are being used. Most of them, like this here, you have the infrastructure, where you have all villages. Okay, so what is the target for this project? The target is, like I said, it must have an objective in your design of your microgrid. Okay, complementing with adequate and sustainable infrastructure. Okay, and to help on the social and economical improvements. Okay, and then communities to produce local expertise, for their own. For example, some farmers, some they use, and shall be adequate and reliable, available to operate on 24 hours basis supply. It must be cost effective and competitive. It should be expandable or modular, okay, for future developments. So this is some of the modes of the rural electrifications. So most of the time, you see, grid extension, one of the options, standalone diesel generators or standalone PV systems. Alternative, you can have a microgrid, which is a combination of PV, wind, mini hydro, biogas, or biomass or storage. So this is for rural electrifications. So these are the options. And let me give you an example. This is actually a real example where we have the biomass, which is actually using this biogas. We have the mini hydro, and then we have the solar. And then this is a real systems, where the project configurations is a PV array. It's around 850 kilowatt peak. The inverter also, it's sized around that range, which is around 850 kilowatt. The battery is 4,500 kilowatt hour battery. Diesel generators, there are 4 sets of diesel generators. 2 of them are 450 kilowatt, and 2 of them are 350 kilowatt. And these are developed under the Ministry of Rural and Regional Developments. Okay, and start designing in 2010, and then the design finished in 2012. What you can see here, you can see in this slide, maybe the pen. So you see here the 4 1 2, 3, 4, the diesel generators. Okay, you can see the 850 kilowatt photovoltaics, and you can see the storage. This is the storage where all the batteries, and then you can see the control panels here. Okay, so this is a typical microgrid, where it is what you call it's still working and it's functioning at the moment, and it supplies the water to the electricity to the remote area. So it is a hybrid PV battery microgrid. Okay. This is what's under the PV panels is the same example. Okay, this is another smaller system. Okay, where you can see you can see it's all in the mountains, in the villages, where there is no grid. So you can see the solar. You can see that we have inside here we have the batteries. Okay, so it is a battery solar only. There is no diesel generator in this. Okay, another example, which is also consists of battery PV array around 200 kilowatt peak. The inverter is 100 kilowatt. Battery is 720 kilowatt hour, and then we have 2 diesel generators of 200 kilowatt and one at 250 kilowatt. So this is another example of existing microgrids. Different combinations, as I say, depends on the locations. And also there is this is another example where we have wind. Okay, because here this area you can see here is facing the sea. There's a sea here, so they have a good wind access. Okay, where the solar is 100 kilowatts. Wind turbine, there are 2 wind turbines of 100 kilowatt each. We have an inverter of 125 kilowatts, an inverter of 90 kilowatts. Diesel generator, there are 2 of 200 and 1 at 120, and then the battery at 480 kilowatt hour. What you can see, maybe I will reinforce what I have mentioned yesterday about the dependency or the reliance on the local resources that's available. That's very, very important. Means, for example, here we have access to the wind, then the wind becoming an option. Okay, then we have wind, PV, battery, and diesel generators. In just now the locations, we don't have, for example, this one. They give you this one here, this one here. Here, it's only PV and battery. Why? Because the area is very remote. Maybe the access to diesel, it's becoming challenging. So the design, it's only the PV and the what you call battery. So, and then here, for example, we have the battery where we have access. Here we have another resources, which is the wind turbine. So these are the different combinations. Plus, we can, like the different configuration, like we said before, we may have either DC configured as grid connected or isolated, but all of these are isolated. You can see all of them are isolated. Okay, all right. So these are some benefits for rural communities. Okay, I think the socio-economic improvement of the community. And the people will stay in this kind of remote areas where they can do their own farming or whatever, the quality of life. Okay, that's very, very important. Quality of life will be improved because access to electricity will give them access to communication, access to, for example, internet services, where the kids can study longer, can hospitals or can keep medicines, for a longer time. They have storage for medicines and clinics and so on. Okay, and also one of the things which all the government is trying to go is to reduce the gap between the urban and the rural areas, which are actually a big challenge, because there is a very big difference between what people in the cities have and what people in the things, okay? And giving basic to social and physical services are available. Okay, I think maybe I will end up, maybe I give you another example, maybe before I open for questions, and then we can move to the next one. Maybe, okay, discard. Let me pull out the next presentation. I think maybe I will give another example here. This is another example in the United States, okay? In the one of the institute in the United States, one of the IITs in the United States, not IITs India, but I think Illinois Institute of Technology. So this is actually a microgrid system, okay? It costs around 14 million project, okay? With a microgrid, high reliable, okay? And it has, because this is designed for research also. They have a lot of Zigbee sensors because they want to monitor and do the reading. So this is the configuration of the system. Okay. So if you see, this is the microgrid. So we have here. That's why. So as you can see here, we have the storage. They have batteries. Okay, electric vehicles, charging station, and they have what you call gas turbine generators, a PV and wind. Okay, and also they have a lot of sensors which on the buildings. Okay, and then also on the distribution networks, distribution control. So like I said before, they have different control levels. Okay, so here it's, for example, the economic operations, how much that we can buy from the grid and sell to the grid. Okay, and then here they look into short-term reliability. For example, if you want to operate on islanded mode, and then we have the microgrid component. They have wind, storage, HDRC switches, building controllers, gas turbines, and so on and so forth. So these systems, it comes in two phases design. The first phases, they have around 362 customers, 2.5 megawatts of load, battery storage and PV, and mobile generator for testing purposes. Phase 2, 748 customers in total, 5.2 incremental megawatts of load, sufficient DR to meet the load. Means they have distributed the renewable energy sources to supply the load, which is quite good. Okay, so these are some of the examples, okay, of what you call some of microgrids that has been been used. Maybe I don't know. Before moving to the next topic, maybe we can open for a couple of minutes of questions, maybe 5 minutes, and then we move to the next topic. Any questions? Is it possible, Dr. Siva, to open for viewers to ask questions?
Yes, Professor. Maybe is I audible, Professor?
Yeah, a bit soft.
Okay. There is a question.
Yeah. Okay. Now clear. Yes, clear.
Yeah, it is an audio. There is a question by Bala Murugan in the chat box. I need clear difference between the interconnected microgrids and hybrid microgrids.
Okay, good. Okay, let me go back. I think that will be a good. Okay. Okay, this one. This is AC, and then we have DC microgrids, and then we have hybrid. Okay, so this is a hybrid microgrid. Hybrid microgrid. The word hybrid here. Can you see the slide?
Yes, Professor.
So the hybrid means is a combination of two different types of microgrids, AC and DC. That's why we call it hybrid. Okay. Okay. So this is the first difference. So that when we see hybrid means it can be interconnected microgrids. Okay. Okay. But maybe they have DC AC, different AC and DC. Okay. But the main important component in hybrid microgrid, it has to be AC and DC. It's two types. Okay. When you have interconnected microgrids, okay, when you have, for example, like the example I've shown you here, for example, both of them are AC microgrids. Okay. So they are interconnected, but they are not hybrid. Okay. But you may have interconnected microgrids which is hybrid also. Okay. So it's possible. So this is just to, I know it's a bit confusing between hybrid and interconnected. And when we see the interconnected microgrids, means the grids are connected to each other. For example, here, if you see here, this grid is connected to this grid, you know. So they can exchange the power without going to the grid, to the bus of the grid. Okay, maybe I think maybe I will go back to the other one.
Sir, excuse me, sir.
Yes, please.
Sir, can I call it a hybrid microgrid as an interconnected microgrid?
Sorry?
Can I call?
I didn't hear you. Can you repeat the question, please?
Sir, can we call the hybrid microgrid as an interconnected microgrid, or we can't call?
Yeah, but okay, they can be called inter-microgrid. Okay, we can call a hybrid microgrid as interconnected microgrid if they can exchange the power without going through the main bus.
Yes,
okay?
Sir. Even hybrid microgrid also the power can be exchanged. No?
Okay, let me show you this. I think I'll show you this one. I think that explains better. Let me show you. Can you see this slide?
Yeah, yes.
Okay. Yeah, actually, you can see. See here, what we have here. We have one common point. Okay. This is what we call networked microgrid. You know, so we have one common point, and then they are connected, so they can exchange. Yeah, actually, you can call it you can call it as a networked microgrid. Is a hybrid microgrid. Is also because they can exchange the power anyway, because they have the power, the bidirectional converter. So maybe during the energy management strategy, when you do the energy management, then you can exchange the power. Yeah, I think very true.
Okay, then what's the difference between these two, sir?
Sorry?
Why we call interconnected microgrid? Can we call as it is a hybrid microgrid also? Why we call it as interconnected?
Yeah. I know. I got your point. It's a bit confusing, like I said just now. It's a bit confusing that we have hybrid. Like I said, the hybrid one, it has mainly must have a DC and AC. All right. Okay. This is the must. But interconnected microgrids, you can have all of them are AC. All of them are DC. That is called also interconnected microgrids. You understand what I mean? Or not?
Even that interconnected microgrid also contain AC microgrid as well as DC, no?
No, but we cannot. We can call that maybe easy. We can call a hybrid microgrid as interconnected microgrids, but we cannot call interconnected microgrid hybrid microgrid. Okay, I think that's make it easier.
Okay,
is it clear?
Clear.
Yeah, it's like it's not exchangeable, you know. Yes, when you're having a hybrid microgrid, we can see it's interconnected microgrids, but we cannot call interconnected microgrid as a hybrid microgrid unless it has DC and AC. All right?
Okay, sir. Thank you.
Okay, good. Any other questions?
Like that.
Yeah, Professor, there is a question in chat box.
Yeah, let me, maybe I can read from the chat box. So to go to the chat box, okay, yeah, there are quite a number of them, I think. Yeah, so display setting, question is, whenever the sources are connected together to perform the microgrids operations, the sources need to be converted from one form to another form. Means a lot of conversions and inversion processes. Do you think that those losses? Yeah, as I say, I think that's very true. Very true. That actually that's why I say the hybrid microgrids are very useful, because hybrid microgrids actually reduces the conversion stages. For example, if I have a DC loads and then I have a DC source, I can directly supply to the grids, right? So this is actually reduced. So that's why when you're having a source that matches the load, that is the hybrid can solve. Reducing the power electronics conversions actually reduce the losses. Very true. And they also reduce the cost. Okay, all right. So and reduce the harmonics in the system. Yeah, automatically when we do rectifications and inversions, there is a harmonic, so that actually reduces. So that's why sometimes the concept of having like subsystems, or we call it sub microgrids, which operate on DC and connected to DC, that will be very useful. Okay. And then, how is an active distribution networks different from networked microgrid? Are we moving back to centralizations? Yeah, not really, actually. As I said, in terms of the control of these microgrids, there is three levels of control. Okay, so you have the control on the microgrid itself, and this microgrid can be disconnected anytime, can be isolated from the other networks. Yeah, but maybe when becoming big, yes, but we are not moving back to the centralized back, but we are looking maybe to a larger system, but with flexibility of operating in isolation at any point of time. Okay. Is a hybrid. Good morning, sir. In terms of power capacity, please let me know the difference between microgrid and interconnected microgrid. I mean, I'm not sure if I get him correctly. So in terms of power capacity, please let me know the difference between microgrid and interconnected. Yeah, interconnected microgrids become bigger for sure. It means, like we said just now, a microgrid can range from a few kilowatts to megawatts. So when we have more connected microgrids, means the power level increases significantly. Okay. What means by power flow management control? Yeah, power flow management control means where the power. For example, if I have two sources, okay. For example, to store it in the battery, or to supply the load, or to on the diesel generators. So that's how the power management. Any microgrids, they have to have a power management control, which manages the power actually. You may create different scenarios and then see. Okay, for example, if you have the power that comes from one source to another source, where the power goes at any point of time, at any point of different scenarios. Difference between microgrid and. Sir, I need a clear difference between interconnected microgrids, and I think we have explained this just now, Bala. I think we have discussed that in very clear. I think, Aniki, good morning, sir. In terms of power capacity, done. How is an active done? Yeah, I think all the questions, I don't think so I have missed anyone, Dr. Siva.
Nothing, Professor. You have answered our
You got
question.
any other things? Otherwise, we can move to the next topic.
Yes, Professor.
Okay, so we have another 30 minutes, right?
Yes. 30 minutes, is it?
Maybe. Okay, so I think we good. So let me go to gain. This is lecture number 2. Okay. Dr. Siva, once I put on the slide mode show,
Yeah.
I cannot see the questions. Is that
No problem, sir. You can't see it also. You are in the presentation, right? Your screen of
You cannot see,
it come up.
Oh, okay.
No issue.
Okay, so I think sharing entire screen, share, and then we go to the lecture, and then display. Can you see?
Yes. Yeah.
Okay, good. So I think we have quite a good understanding on the microgrid, the configurations, the type of microgrids, the benefits, and some of the examples of existing microgrids. Okay, one of the most common, I can see 80% to 90%, if in these microgrids, is the photovoltaic. Okay.
Professor,
Yes.
this particular session will be in the after 11 maybe.
Sorry?
See, this particular session of power voltaic in microgrids is at 11.
Yes, correct.
Yeah, what we do was, is there anything like to emphasize more on the microgrid technologies, like you can do it?
Yeah, it means we start this one later, right?
Yeah, correct.
Yeah, can, yeah.
Maybe you can emphasize more on the microgrid technologies. Check if it is anything left out.
Yeah. Okay. So maybe I will give continue these examples. I think that's a good. Yeah. Yeah. I think I take this. Yeah, I think this one would be good. Yeah, I think I share this one. Let me share this. Screen, touch screen, this one, share. And then I go to PowerPoint, this one. Okay, can you see the slide?
Yes.
Okay, so I think one of the main, I think, what you call the discussion, which is the self-healing capability. Okay, we have the microgrids can operate in 2 modes. Can be operate on a normal mode and also can operate on a self-healing capability. So what does mean self-healing capability? So that's the question. So if you look into here, this configurations here, we have the microgrids connected, but self-healing capability means the microgrid is able to self-heal without the intervention of other sources. For example, maybe another grid, what you call, for example, here we're having wind turbines, we have a PV, solar, and then we have micro hydro. Different sources. You can see here PV, wind turbines. So different. And then, for example, there is a fault somewhere in one of the buses. Or one of the systems. So this microgrid should be able to self-heal, means without interrupting the other microgrid operations. And this is also very important. And maybe I will give you an examples in terms of restorations of with dynamic and static, because static microgrid versus dynamic, we have 2 types. For example, the static microgrids, the boundaries and the connections points are with external systems, and the energy resources and managed in static groups operations. So dynamic, dynamic electric boundaries and connections points, so external, so the energy can move from one to another place. Let me. I think there is another example here. So this is an example where there is a fault. Self-healing mode for a single fault. When if we have, for example, if you look into here, we're having there is a fault happens at a certain point of time, and you can see one of the microgrids some of the microgrid disappears. Okay, we have, for example, MG1 to MG6. There are 6 microgrids here, okay, for a single fault, okay, and then after some times when there is of self-healing capabilities means there are total of 9 microgrids. Okay, so means if the fault can happen in multiple grid concepts. So I think maybe this one. Let me show you. I think this one is quite. The example. We go back to the example. So these are some of the research papers actually. Some of the research for this. Yeah, we go here. Yeah, I think. Yeah, I think we can. I don't know this the control. Maybe we can move to. Yeah. Yeah, I think this is also there's one questions on this on the decentralized coordination of networks. So what you can see here, for example, different microgrids here operating independently compared to others. So you have one microgrid here, another microgrid here, and then we have the what I call the point of common couplings which connected. So this is also a complete decentralized fashion. Okay, it's a completely decentralized. So that to solve the problems if we have a bigger anti-microgrid. This is also actually you can get it from this paper. So yeah. I think there are different energy management, coordination, to how to do the energy management. So, for example, you're having 3 microgrids here, which connected to the bus systems, and then you do the different energy management. Depends on the, for example, how much you buy the electricity, how much you sell the electricity. So different scenarios, okay, and then you decide. Either to sell or to buy or to consume from the neighboring microgrids. So, for example, here you can see the power can be shared between the microgrids without going to the grid. Okay, so for example, here it's between the grids, between the microgrids. Okay, and this is between the grid itself. Okay, so here you can see here, this is the cost of electricity, and this is the cost if you buy from the neighboring microgrids or you sell to the neighboring microgrids. Okay, right? So that's why I say the energy management or the coordinated energy management of this, when you're having more than one microgrid, it's becoming very crucial, and it's important to this. And yeah, maybe we go back to the control. Maybe we can look into yeah. So as I said just now, I think the control of microgrids, we have 3 levels, okay, of control. We have the tertiary controls, which is actually controlling the optimal operations in both operating modes, okay, and powerful control. The secondary control, and then we have the primary control, which is responsible on the voltage stability and the frequency stabilities. Okay, and then you have the connections. This is the microgrid, and then you have the connections to the main power grid. Okay, and the function of the primary control maintains the voltage and frequency. the secondary control, okay, compensate for the voltage and frequency deviations, and the tertiary control is managing the power flow between the microgrid and the main grid. So in any microgrid, you will have these levels of control. Okay. Yeah, and this is the explanations of each of the control. What's each control? And in this kind of controls, we have a variety of control techniques that can be used. Okay, it's not necessarily a single what I call control, but there are a variety of control techniques that, for example, if you look into what you call, you can use the classical control techniques, or you can use also even machine learnings, or what you call new techniques, to control this microgrid, especially when you're having a large number of microgrids connected to each other. Okay. Yeah. So this is an example of the hierarchical controls. Okay, where this is the, so when you're having the main grids, so you will be set. You must have what you call the PLL, the phase loop, which control, and then you measure the active and the reactive power. Okay, and then you put it in the tertiary control, and then you feed it back, connected to the secondary control. Okay, and then you have the primary control of each DAR. So each DAR will have its own control. You can see the concept, and then we have this here, the point of coupling. So if you look into from the primary, for example, if we have a DAR here, 1, 2, 3, 4, 5, 6, 7, 8, depends. For example, if I have a PV, a photovoltaics. So what my primary control do? Primary control is try to work or to push the PV panel to operate at the maximum power. Okay, and then stabilize the voltage that's output of the PV. So we may have an MPPT control for this photovoltaic system. Okay, and that's actually maintains the voltage level that can be generated. For example, if you have a wind turbine as another DER, so what does this? You can have also an MPPT control. You may have a pitch control. You may have, for example, if the wind speed goes very high, then you have the pitch control, whatever. So that to maintain the power that comes from the wind turbines. Okay. For example, if you have the battery, so your battery control system's primary control is, for example, maintains the state of charge. So we cannot overcharge and we cannot over discharge the battery. Okay. So this is the primary control within the things, and then you have the secondary control, okay, which is actually linked to between the DARs, and then you have the upper level, which is the tertiary control hierarchy. Okay, I hope it's clear. Is there any questions on this? Because this is very important to understand how the control structure of the any questions?
Yeah, this hierarchy is essential for the microgrid, Professor.
Yes.
How about?
But here, okay. If you don't have the grid, for example, okay. If you don't have the grid, so what you don't need? You don't need this control anymore, right?
Yeah. Yes.
You can see here. You can see you can isolate, and you can see here. You can see islanded, or you can have grid connected. So if you don't have, so you can remove the grid, because what we have, if you don't have grid connected, so what do? You need to have the control of each of the DER, right? For example, you have a PV, right? You have a DC-DC converter, maybe you have an inverter. So that is the control, that's the primary control. And then on the upper level, when I want to communicate between the PV, the wind, and the storage, so I have another energy management control. Okay, please go ahead.
Yeah, the secondary control is more than enough to go for a microgrid. Is it not?
Yes, but if it is not grid connected.
Okay.
The secondary control will be enough to operate the microgrid if it is not grid connected. But if it is grid connected, yes, you need the tertiary control. Okay. Any other questions? And we will be discussing some of the primary control techniques. For example, when we look into the photovoltaics, and then when we look into the wind, okay, and then when we look into the batteries, for example. So we will discuss some of the control techniques that can be used as a primary control, because the most important control here is the primary control. So if your DER operates efficiently, okay, so you will be able to, to extract the maximum power, because the objective, as I said before, the objective is to maximize the renewable energy factor from this microgrid.
And then the energy management control also, when there is a grid only, it is involved.
Sorry?
The energy management control
Uh-huh.
it is required when the grid is connected.
No, even without grid connected, you need the energy management, because you need to, for example, you have a PV, wind, battery, and diesel generator. Okay, for example. Okay, so when do you want to turn on the diesel generator, for example? So you need to have the management, the energy management within this, because you have, for example, you have power that comes from the PV. So that power PV goes to the load or goes to the battery. That's power. Okay, example, you have less power. Suddenly, certain load turns on. So where does power come from? Does it come from the battery or comes from diesel generator? You have to turn on the diesel generator. So when the state of charge of the battery goes low, where this battery charge, we have to turn on the diesel generator or what? So this is what I call the energy management within these resources.
Okay.
Okay. But when the grid connected, so now we have another player, which is the grid. That's why we need to measure the P and Q of the grid, and then use them, and then feed them back to our control to try to control and try to maintain how much power we inject to the grid. All right. Any other questions?
One question is, there is a chart box I'll read out, Professor. Is V and voltage and
Sorry?
frequency?
Huh?
There is a question in the chat box. I will read out, Professor.
Okay. I can maybe let me check.
Yeah.
Maybe I can stop the thing and then go to the chat box. Okay, where is it? The chat box. Okay, yeah, here. Is V and F secondary control and power management? Is V and F secondary control and power management is tertiary control? I don't understand. Is V and F
The voltage and frequency.
Yeah, I understand. I know. I understand what he means by the voltage and frequency. Let me go back here.
Yeah.
So, like I mentioned before here, so the primary control maintains the voltage and the frequency stability of microgrid subsequent to, for example, island mode. So like this is controlling the microgrids. The secondary control compensates for the voltage and the frequency, and the tertiary controls microgrid. Okay, and the main grid, and facilitate economical operation, to sell, like I said before. I think I've shown one example just now. Where is it? I think this one. No. Where is I showed the examples. Let's see. to see the operation, you know, is it to sell or to buy from the grid? This one. Yes, this one. Yeah. So this is what you call, this is what the energy management do, you know. So is it to sell, to buy? Okay. So we can see here there are two. Let me share the screen. Let me this. Then use the pen. Okay, maybe the pen. Okay. So what we have here. So you can see here these two colors here. These two colors is the price of the grid. Okay, when we buy and sell from the grid. All right. So actually here, for example, 28 cents if we buy. If we sell, is around 30 cents per kilowatt hour. Okay, and this one here, the blue and the red, is between the microgrids. Okay, for example, sell and buy from microgrids. Okay, so here you can decide. Okay, so you can decide actually where you want to sell your power and when you want to sell it. So this is what I call this one here. The control that is here is the territory control, which deal with this. Okay, secondary microcontrol deal with this. Okay, primary control deal with this. Okay, I hope it's clear. Okay, maybe you can see maybe this card. Other questions? Is there any questions? Sorry for asking. As one of the, can I consider plug point as one of the grid? You mean the plug point here? Do you mean that plug point is connected to the grid, or it is like a load? I don't understand. If it is connected to the grid, then yes, automatically then it is the grid being that your system is already connected to the grid. If it is a grid, is the plug point is a grid plug point, and then you connect your microgrid to one of the microgrid to it, then your grid means your microgrid is becoming interconnected to the grid already. But if you mean your question, is it a load? Then no. Okay, all right. I think any other questions? Please ask. Please, any thing we have discussed quite a number of topics here now. Before we move to the next one, then we. Difference between power flow management and energy management. Power flow management. Yeah, actually, it can be used. It can be used similar. Energy management. When we see the energy means actually the power and time. Power means talking about voltage and current. So when we manage the energy management, means we manage the energy within the microgrid. For example, you consider the time factor, but it can be used. It can be used similar. For example, power management. For example, when you control your bidirectional DC-DC converter, that is a power flow management. But when you control, for example, where the power comes from this microgrid to this microgrid, that is what I call energy management. So this is the energy management for the overall systems. Okay, power flow mainly controls, for example, the bidirectional, for example, converters. Energy management is the total, the total energy within the grid. But sometimes we use them the same, actually, to be honest. Sometimes we use power flow management or energy management, it can be used the same. But usually, specifically, power management is mainly for the power converters. Okay? The energy management, which is the whole, for example, including or excluding the what you call the power converters, especially the bidirectional power converters, because we have in interconnected microgrids, especially hybrid ones, we have a lot of bidirectional converters, which has to be controlled also. Yep. All right. Any other questions?
Sir, I have one doubt.
Yeah. Can you increase the voice?
In microgrid categories, you have told that for commercial microgrid, the
Sorry?
rating should be in commercial microgrid, the rating should be greater than 50 kilowatt.
Yeah.
Similarly, for campus or community, it is of 1 to 10 megawatt. For unity scale, it is greater than 10 megawatt. Is there? It is a standard, or we can? Is there a,
No, it's not standard.
on
It's
what basis you are telling that it is greater than 50 kilowatt, or that range? How are you telling that, sir?
no, it is not standard, but this is just the definitions. When we, at least when you know what is that commercial, community, and then utility. But you can have a microgrid of, as I said before, of 5 kilowatt. You can have a microgrid of 10 kilowatts. You can have, so you can have the sizes. Actually, it doesn't matter. But that's the definition for commercial. Commercially means you want to sell, because if you have a 5 kilowatt, most of the time it's just to supply your local loads. Okay, you are not commercially selling or buying the electricity from the grids, most of the time. But if you have you want to sell power, then you will be needing, large systems. So that's the difference. But doesn't mean that you cannot have a microgrid of less than 10 kilowatt. Yes, you can. All right.
Okay, sir. Thank you.
Thank you. Any other questions? I think if there's no questions, maybe we can have a break. Dr. Siva?
Yes, Professor, we'll start again back at 10:30. 11.
11 means
Yeah, I'll tell the timings.
4:30, right? Sorry.
Just a minute.
4:30, right?
30 minutes later, sir.
Yeah. Let me see.
Yeah, 4:30. 4:30, correct.
Yeah, 4 o'clock area. Yeah. Thank you. Okay, see you after 30 minutes.
Yeah.
Thank you. Thank you, sir.
Bye. Take care.